great collaborators, great country. That's a bit too far. Yes, so I'm going to talk here about hierarchical probabilistic forecasting. So I didn't put all the details in these presentations, but if you have questions, please don't hesitate. So just acknowledgement, co-authors, James Taylor from Oxford and Rob Hyman from Monash University, and we have a paper under review, which has application in case studies. So I'm going to talk about that. But we also have other development related to these problems. So if I have time, I will talk about it. Okay, so I guess I don't need to remind us the challenges in the smart grid, but essentially with renewables, with the uncertainty in demand for different households, we clearly need some quantification of uncertainties, and we will see that often we don't need just the demand for one household or the generation of one turbines. Often we are interested in the total or in aggregations of these quantities. Okay, so that's essentially the main motivations here. We want to quantify the uncertainty of aggregates of these quantities. And just a picture would be this one. So here I'm going to focus on electricity demand. And essentially, we have the historical observations for each household from 1 to t. In our case, t will be very large, a year of data every half hour. Okay, so I'm interested in forecasting so the demand, the electricity demand, or the wind or the solar or anything for each household, plus for some aggregation and aggregation of aggregation. Okay, so that's the total demand, that's the individual demand, and then we have aggregations here. One thing important to note here is this is a very simple examples, but typically you could have possibly millions of smart meters here, and also the depth of the tree. So the tree could have a high depth. Okay, so you could have like here just we have two levels, but you could have many levels. Okay, and I mean fundamentally this problem is quite simple. Like, if you think about it, what we are doing is just forecasting, so multivariate forecasting with aggregation constraints, right? If you want to define it, it's not very fancy, right? You just have some aggregation constraint, and the question is, how do you do that? Is it easy? Adding the constraint, does that help the forecast? This kind of questions. And of course, it doesn't have to be hierarchical constraints. Okay, I have examples where it's not hierarchical. So, just as a note, although I'm going to talk about electricity demand forecasting, I see these applications, I would say these applications is even more interesting because imagine you have some smart grids, or imagine each household has solar panels, wind turbines, so you have generations and you have consumption. So what you are really interested in is generation minus consumption, and you want this to be always strictly positive, for example. And in that case, of course, you want this to be always positive, but then it could be that this is positive, this is positive, this is negative, and this is positive. So it means that you need to do something here. You have to be careful, like for the next step ahead. So just as a note, keep in mind that although I'm going to talk about this application, I believe there are many others. If you think a bit more about the problem of hierarchical forecasting, you could find very interesting applications that are more relevant than the one I'm going to talk about. Okay, so keep that in mind. Before talking about this problem, I just wanted to mention that this problem is quite general. So I gave a talk last year at Amazon in Berlin, and they had exactly the same problem. They sell a lot of products, and they are interested in aggregation of this product at different level. Different departments need different forecasts, and it has to be coherent. Okay?
And also suppliers, I guess, right? Because they get maybe a bunch of product for a certain supplier and...
Yes, I guess, but in their applications, what we talked about, this was more about the products. But of course, yes, you have this, it's like generation and demand.
Yeah.
You have suppliers and you have consumption. Yes.
Yeah.
Another applications, that's a grant which is finished now, we had from Huawei. And in their case, it was even more complex because it wasn't hierarchical. You had a graph of dependencies. So for example, to build a phone, you need a screen, you need, I don't know, you need some aluminum, you need multiple products to build it. Now the question is, suppose if you forecast that tomorrow you need 100 phones. This means that you need all the products multiplied by 100, etc. So that was another interesting applications. Another applications was Coca-Cola. So they had the number of bottles for each country and then each city, etc. And they were interested in having this coherent. The message here is that this problem is quite general. So here we are going to talk about energy, but keep in mind that it's quite general. So if you can build some efficient algorithm or estimation methods, then many industries would be interested to use it. Okay, so Pierre asked us to talk about the data we use. So here it's the electricity demand data from the Energy Demand Research Project. You can download it after registration, so it's free. I mean, we didn't use the entire data set, but you have more than 14,000 households, half-hourly observations for more than 2 years, almost 3 years, right? You also have geographical information at higher level, so you don't have latitude and longitude, right? You have maybe postcode until postcode, and they guarantee that in each postcode you will never have less than 3 meters or something like this.
I have a question. So
Yes.
that's the same data that Stephen...
Yes, I think it's the
mentioned?
same. I think it's the same.
Okay.
I'm not sure, but since he said 14,000, I think it's the same. Yes. You also have they call it ACOM segmentation. Essentially, it's segment the population in different classes. Those that are rich, not rich, those with family, with the types of job, etc. So you could use, if you are looking for a big data set with smart meters giving you geographical information plus segmentation, I think it's a nice data set. But it's messy. So that's the reason, this motivates the third point. Yes?
Sorry, just to finish, what about what's geographic information?
Okay,
Because that's what
they call it NUTS, N-U-T-S. It's that's the name. If you Google NUTS geography, it gives you essentially. So the UK is divided into different regions and then sub-regions, etc. According to this NUTS nomenclature. Yes, that's it. So you have
British friends, can you explain what a nut is?
I've heard of it.
Yeah, so it's
Okay, it's really precise.
yeah, exactly, that's the one. Exactly, they call it NUTS.
like in say,
Because it's Europe-wide thing, I think. Nuts. I thought there was nut zones Europe-wide. I thought. I didn't realise it was particularly a UK thing, but maybe I honestly don't know.
Okay, but so how big is the nut?
Well, I think actually you have maybe you start with 10 roughly, or not even 10 even. I think 4, and then in each of them you have I don't know 7, and then each 7. So it's like a hierarchy.
So it's a tree. Okay.
Yes, it's almost like a tree.
Okay.
Yes. So okay.
Cool.
What we did is we just selected 1,578 meters for that period. Well, actually, I did that because essentially for this hierarchical forecasting, we needed the data to be aligned, and that's showed already an interesting problem. How do you do hierarchical forecasting with non-aligned data, right? So in this case, for example, I had like 1 month missing and then missing values here. So, but if you try to sum this data, well, the top is completely missing, right? Because, or even if you try to replace, suppose you try to replace your missing values, then the number you get here is, the uncertainty you get at the sum is very high because you have so much missing values. So that's already an interesting problem to think about. Yes, and that's just for the experimental setup. So we use 12 months for training, and then the next 3 months for evaluation. Okay, and our problem here is 1 day ahead forecasting. Since we have half-hourly data, it's essentially 48 lead times. Okay, so that's our problem. That's actually our hierarchy. So the way you read this hierarchy is that's the top, that's the child nodes, and then that's the child nodes of the childs, etc. And that's all the meters. It's a circular visualization of your tree. Okay? And the number gives you, I think the number gives you the number of aggregations you have. Okay? Yes. So you can see there are some small aggregations, some are larger. This was not on purpose, but it's interesting because in practice this will happen. You won't always have this nice full tree with the 20 aggregations everywhere. Sometimes you will have a few, but then sometimes you will have like 100 aggregations. Okay, so that's our hierarchy we are dealing with here.
We discussed it to make a parallel with the wind farm. I think Jetro mentioned that you would have this thing like you have offshore wind farms where you have two big ones.
Okay.
Under one subnode, and
yes.
then you would have another area where there's lots of dispersed turbines on shore. And so
yes, and that's challenging also for the algorithm. We'll see. Yes.
The measurements are only at the lowest level. There are no measurements, let's say, at intermediate.
That's a good point. So here, you are right. Here we measure this, and then we just sum. But you are right. In practice, you could think about applications where you get some data more frequently at different levels, and then you can use already data available. The others, you have to wait for it. Yes.
Yeah. Well, I think it's really important in this application as well because what you measure at the first aggregation will be subject to the losses on the network, and the losses themselves depend on demand on the network and all the rest of it. So and all the applications here are around managing resources and the network, right?
Okay.
So I think there's that added complexity in the energy network that maybe isn't here in the the supply chain or the
definitely
stock management where you do observe everything all the time and everything is always perfect provided.
Yes, if you just add, you want to make this problem, it's already complex, we'll see later.
No,
but
sure.
but if you want to just make it more complex, just add missing values.
Yeah.
Plus, if you add the fact that you don't observe everything, so your data is not anymore coherent, then why would you want to make your forecast coherent? So you have new questions, because the assumptions here is your data is coherent, right? The sum of the bottom is equal to the top. But if you start with incoherent data, what's the motivation of trying to make them coherent? Yes. Okay, so here is an example of data we look at. So that's a smart meter. 1 week of observations for 1 smart meters here. Then you aggregate with 10, and then 30, and then you can clearly see that it becomes smoother, and you have the 2 typical peaks of electricity demand. And you want to model this. Actually, it's not really modeling. So I think in this hierarchical forecasting, we have to be careful because you have some nice statistical models like hierarchical models, which already have this framework of modeling things at different levels and all that. It is not really modeling. It's more, we are interested in forecasting all of them. I think it's 2 different problems. Okay, so here's another example where what I'm showing here is the average consumption, daily consumption, and you can clearly see here that Sunday people sleep a bit more, right, compared to other days, etc. And you can clearly see that this seasonality disappears with the disaggregation. It's there, it's just you don't see it anymore. So that's for the top one, and that's just for I just took one meter. Okay, so how do we represent this hierarchical time series? Well, it's not it's very easy. So if that's a vector of all your observations at time t at the bottom level. Okay. But since you are interested in both the bottom and the aggregates, well, you have the identity here. and you also have your aggregations here, right? And that's the vector essentially you try to forecast, right? That's at time t, and essentially you have observations from time t equal 1 to t, and the goal is to forecast what will happen at t plus 1. So you want the entire vector, okay? Just one note, it doesn't have to be binary, okay? You could, what I will present should work for any matrix that can be read, for any S matrix. You could have, except the identity here, you could have negative values, it would work, okay? So in terms of forecasting, what you need is, well, mean consumption. You know that essentially mean forecasting reduced to estimate the conditional mean, which means fundamentally what you need is just the conditional mean at the bottom. If you can produce the conditional mean at the bottom, it's done. Just produce the conditional mean at the bottom and sum. So again, there is nothing special here. If you can do it, then the problem is solved, right? You just multiply by s and finished, right? Well, we will see that. The problem is that you have estimation error and all that, okay? And for probabilistic forecast, what you want is, well, here it's a bit, you have to be careful here, because what does that mean to produce probabilistic forecast? Even the definition, does it mean that you need the joint distribution is vector? Yes, but you have sums, so it's going to be degenerate. Do you need just the marginal at each node? Okay, so we have to be careful. What does that mean to produce probabilistic forecast? Here, what we want is just the marginal at each node. That's the way we define probabilistic forecast. Okay. Of course, if you ask the marginal at each node, the dependencies between this household and this one might not be correct, right? Because you didn't model everything, but that's fine. I mean, having already coherent probabilistic predictions for each node is the first step. Okay, now methods. How do you do that? Well, it's simple. So the natural things to do is bottom up. So what does that mean? Try to compute an estimate of that guy. Well, we have already many methods that allow you to do that. You could use VAR models, you could use deep learning, you could use whatever. So compute this, and then just multiply by S. Now, in practice, you could also just forecast each node at the bottom independently and sum. That's fine. It's just an estimate, making assumptions. It's an estimate of this quantity. Okay? That's bottom up. And then Bayes, what we call Bayes, this is also very convenient because you have all the sums at the bottom and the aggregates. Let's forget everyone independently, all nodes independently. Why is that nice, or why does that work in practice? Well, because the data at the top is very smooth, so you should use, even in electricity demand forecasting, if you look at the literature, you have some methods that works fine, that works well with aggregated demand data, and you also have different methods. You should use different methods when it's very disaggregated, right? So this approach allows you to do that. You just forecast each guy independently. Okay, so what are these advantages and disadvantages between these two methods? This one is just a plugin estimator. The problem is that you are trying to model these conditional expectations with possibly very disaggregated data. So this estimate will typically not be good, right? Because at the smart meters level, your data is very noisy and all that. So you are going to sum these bad estimators, right, or estimates. However, it will be coherent, right? Because you do this sum, you are fine in terms of coherency. Essentially, how do I define coherency? That's how I define it. This is a zero vector, and equality here is pointwise. So I want this to be true. What's A? A is, so remember, the y vector has an A part and a B part. A part are the aggregates, and the B part are the bottom. I want the sum of the B to be equal to the A. So that's what I mean by coherent. So, and again, Bayes, the problem is that Bayes is not coherent. and well, you have a very high probability that it's not going to be coherent just due to estimation error, right? Okay, and there is this trade-off between accuracy and coherency. In practice, although people think that combining things is better and all that, sometimes it's hard to beat Bayes, right? Because if you do the best job at every node, then it's very hard to beat it by coming from very bottom level, right? Even if you do your combination, still you are going to sum a lot of forecasts and all that. So yes, so Bayes is quite good, but then it's not coherent. Now, some authors proposed a combination of these two methods, right? Because what you want is, I want to use Bayes forecast, so I want to forecast everyone, but at the same time I want to make it coherent. How can I do that? Well, that's your Bayes forecast, it's a vector, and using this matrix P, you can see it has combination weights. You combine the Bayes forecast. This Py hat, if you check the dimension, it will have the dimension of B. So it gives you new B's, new forecast for B. Because what's the dimension of this? The dimension of Y is n by 1, and the matrix is m by n. So this will be m by 1, right? And then you sum. So the advantage of this type of forecast is you forecast everyone and you are still coherent, but you have a problem. How do you estimate P? That's the question. So you are coherent, you combine forecast. Oh yes, plus there is another advantage is in the literature many people have proposed some kind of combination methods. And it turns out that many of these methods can be written like this. It's just a different P actually, right? Instead of selecting P, let's try to find the optimal P, right? According to some loss function. Okay, so, well, you try to optimize P. So for example, let's minimize the, let's focus on one step ahead. Forget about H. One step ahead forecast, conditional on the past. Suppose you want to minimize this, okay? Well, it turns out that if you make this assumption, you assume your Bayes forecasts are unbiased, and you try to minimize this subject to your revised forecast to be unbiased, then you have a very nice Poisson solution. I mean, it takes 4 lines to prove it. I mean, it's not very fancy. Well, a little bit more, but you can do that. Now, essentially, by making this unbiasedness assumption, what will happen? Well, your MSE, the bias disappear, and then you have your variance term, and then if you add this constraint, multiple things cancel, and you get this. And actually, when you look at this, you recognize the solution of a generalized least square, essentially, right? So what you are doing is essentially, you are taking your Bayes forecast, y hat, has your response in your regression, and you are taking S has your design matrix in the regression. And of course, you have this W, which is some weights, and that's it. So essentially, to summarize, I would say the state-of-the-art methods to do hierarchical forecasting is very simple. Estimate W, and you get the optimal P that will combine everything, and everything will be coherent. That's it. So that's how you do, I would say. Now, okay, I have to say that I have written a paper recently where, it's not yet published, where I removed this condition and these conditions and get an agreement for that. So just as an advertisement, let's say.
So if you don't show it in your slide, can you tell us the trick for you remove this unbiasedness?
Well, essentially what you do is, so maybe I can write it here. So if you think about, look just at this. Okay, look at this. What I'm doing is I'm looking at the empirical risk and at an empirical risk minimization. So suppose you try to estimate this. So what I'm minimizing is this, is 1 over t, the sum, over t of yt plus h minus y till t plus h. I minimize this. I try to minimize this directly. There are some subtleties here because this is conditional. What I'm doing is unconditional, so you have to be careful. But let's forget about these details. And actually, when you look at this, it's just a multivariate regression problem because you can rewrite this as essentially I'm trying to minimize this. And forget about the S. Okay, S is just the sum. So this is just a multivariate regression problem, right? And you have a closed form solution. And you can even prove that if you just add this constraint without this one, the two are equivalent asymptotically, etc. So it's nice. But the story is that you can remove these two conditions and you have an algorithm for it, and it's reduced to solving a regression problem directly. Okay? So to summarize, we need P, we need to estimate W. Well, choose your favorite covariance estimator. That's it. That's the story of this slide. Just because in the experiment I will talk about shrink and diag is just one that uses a W by using shrinkage, and diag just use a diagonal. That's it. Okay, now, I thought it was short, but I talked too much. The goal here is probabilistic forecast, but I had to introduce mean forecast. Well, actually, this method gives you also the variances. So if you are just interested in mean and variance, done, finished. You don't need anything else, right? Because under these assumptions, you get the variance for free. Well, for free, it's given. So that's the mean. So estimate P, plug P here, and plug P here, and you have the variances. For example, if you want to assume multivariate normality, fine. Then you have your, actually in this case, everything is coherent. All dependencies will be taken into account, right? Now, if you don't want to make distributional assumptions, then you have to do more work. Well, Bayes is also very easy to do. At each node, build probabilistic predictions at each node. Just the univariate time series. You can do that for each meters and for each aggregate, and that's fine. The one question is, how do you do bottom-up? Because with mean forecast, it's easy, you just sum the means. But imagine if you give me density forecast for all the bottoms, just the marginals. How do you do bottom-up, right? And what we really want is, I mean, that's another question. Do you really need probabilistic coherency? We could discuss that. Oh, to make coherent decision, we will need it. Maybe you might say, no, I just need it at the top because the decisions are only done at the top, not at the bottom. That's another discussion we could have. What we want is to have coherency, probabilistic coherency. I define it this way. So I want essentially the probabilistic forecast of my aggregates to be equal to the sum of the probabilistic forecast at the bottom. Okay, so that's the way I define it. I want to be able to model each series independently. That's actually quite important because for some methods you cannot. You must forecast just the bottom and sum. Also, there is this idea that it's easier to forecast at the top. It should be easier because it's smoother. And you would like a method that allows you to do that. Avoid distributional assumptions. That's also something we want. Otherwise, just use Minty and it's finished, right? Why? Because, well, actually, it's a bit funny because with aggregation, things become more and more normal. So normally, you should not have a lot of problems at the top, even if you assume normality. The question is really at the bottom, where your meters can be very different and very heterogeneous. And scalable to large hierarchies. That's also, I think, important. because when you start to model this big hierarchy, you need to at least do something not too naive in terms of computation. Well, let me just talk about a naive way of doing it. Well, it's not really naive actually, it's what you should do. Is suppose this simple example, no hierarchy here. Just, well, actually it's just the sum of the variables. Well, if you can draw samples from the joint distribution, then that's it, at the bottom. Actually, you don't even have, you can compute any function of these random variables, not just sum, right? So in your problem, if you can do that, then that's it, forget about what we are saying here. You don't need these methods. In our case is, no, we assume it is hard to do that. And we also assume something else. We assume that we have good algorithms to produce the marginals. Right? That's another assumption. In practice, we know that I can produce one step ahead predictive distributions with different models. I have that. The question is how to compute bottom-up forecast if I already give you that. Okay? Well, again, well, not again. Actually, so in our case, we don't introduce copula just because we need dependencies. It's convenient because we assume we have the marginals. So thanks to copulas, what we can do is, well, I have my marginals, so and I can estimate my copula. Then I can draw samples from the bottom level and compute the sum. Right? So that's the naive bottom-up. So if you can compute the copula of the entire bottom-up level, then you are fine. Or any approximation. Suppose you know that there are independencies, you are fine. That's bottom-up essentially. So nothing fancy here. Just a note, everything is unconditional here, but when you use copulas with conditional distributions, there are some technicalities, so we need to talk about this. There is a version of Sklar theorem for conditional joint distributions. So, but that's just a note. Okay, so we know how to do bottom-up naively. Now, this is not hierarchical yet. So if you just have one level, fine. And if it's low dimensional, fine. Now, let's do it for hierarchical. Well, again, it's simple. Just draw samples from the bottom and consider this just as different aggregations. You can also do it, there is no problem. The only thing is, we are not really exploiting the fact that we need specific aggregations. Why should I model all the dependencies at the bottom if I know I need only certain sums? Right? You could if you want to be very general, but here I want to speed up things. I know I just want these aggregations, right? That's the first thing. And again, the other problem is, look where my modeling is done, it's done at the bottom. Everything I do is done at the bottom. Why? Is it possible to do something at higher levels that will help me to build the bottom up? So that's essentially what we try to do here. And it's very simple. Well, the algorithm, it takes time to build it, but the idea is simple. Yes?
Okay, so that's what you're going to say on your next slide. Okay, I guess I don't have a question.
Okay.
It's okay.
So, so here is the thing. If you give me the dependence, the marginals for x1, x2, and you give me the copula, I can compute that guy. So I don't need 4-dimensional copula. I just need 2-dimensional. This one is fine. Here I need 2-dimensional, right? But there's a problem. If I just compute the dependence here and the dependence here, I cannot compute that guy. Some things are missing. Well, if you give me the dependence here, the dependencies and the dependence here, I have everything I need to compute the dependency, all the sums. Okay, so essentially I don't need a 4-dimensional here. I could decouple my problem into multiple specific copulas that guarantee that I can compute the marginals everywhere. It's not yet finished because it's easy to say, but then we will see that when you implement it, you have a problem. Yes, that's essentially what I say here, lower dimensional. And also there is something interesting here is I said I need the copula here, and the copula here. So you see now, I am modeling things at higher levels, right? Because think about my residuals at higher levels. How do I fit this copula using historical residuals? They would be more precise, right? Because it's smoother and all that. So that's where you can see already the modeling. Yes?
But you're getting a kind of hierarchical estimation as well. So you have an estimation of the bottom level, then you have an estimation error, and then in your fit, including your estimation error, you're doing your next fit and so on. So you're aggregating the errors as well, isn't it?
Exactly. So it's never going to be completely independent, right? Because completely independent would be compute marginal here, marginal here, marginal here, everywhere, okay? Plus compute copula here, copula here, copula here, copula here, and then apply a transformation on these measures that makes them coherent. That's something we didn't do yet, but if you can do that, then indeed there is no bottom-up happening, although it's there, it's hidden, it's always hidden. Okay, so that's what we want to do. Now, how do you implement that in practice? Because in practice, you would sample, generate a sample here, generate a sample here, and then, well, actually generate a sample here and generate a sample here. Then you would compute the sum. But then how do you inject the copula you computed here? Right? Because do you see what I mean? So let me say it again. So I know that if you give me the copula here and the marginals, I have everything I need to compute the thing at the top. But now, so let's start from the bottom. I sample a two-dimensional vector n times, a two-dimensional vector n times, right? I take the sum. Okay, so I have now two vectors. How do I inject the copula here? How do I inject these dependencies there? So that's something it's not difficult. When we talked about it, it was like, yes, it's easy, right? You need the copula everywhere, but you need an algorithm to inject the copula there, because you cannot just sample from there. It has to come from the bottom, you see? If you sample from here, then that's fine, but it's not going to be coherent. So that's the thing. Well, the idea is actually, it's already available, and we could call it dependence injection by sample reordering. It's essentially something that says, if you apply empirical copula to empirical margins, it's equivalent to sample reordering. So what does that mean? If I go back to my picture here, you sample independently, so here, independently here. You inject the dependence here, done. You sample independently here, you inject the dependence, done. Now you can make the sum, you can compute the sum. So now you have two vectors, you need to inject the dependence in that sum, and then you sum. So if you do that, then you have all the dependencies where they should be, okay? And this goes back to a paper by Ayman and Conover for normal copulas. In weather forecasting, it's also used, because often you have many variables. You want to sample independently from all these variables, and you want to inject the dependence. Okay, and that's what we use. I won't go into the details for that. Okay, so let's see. So there is one thing I forgot to mention. So if we go back to my questions that I said, I wanted this. Okay, I have this by definitions because I'm summing. I can do this because indeed I am modeling each series. I exploit Boyd disaggregated data for the copula only, not for the marginals, because if I didn't use any marginal here, right? The marginal here, I didn't use it, right? It's still a bottom up. So the only thing we did is we applied mean combination. So in our algorithms, we have the bottom up with aggregation and copula, plus we also combine the means. This allows us to combine all the densities. I won't go into the details of the algorithm because it's just not friendly. So forecast evaluation, I will consider CRPS, the quantile score version of the CRPS, but again, I don't compute this, it's an approximation, right? It's a sum over probability levels. And I will also consider this one. This one is quite interesting, the weighted CRPS. Never trust your CRPS. My experience, CRPS is very sensitive to the mean, to the center. So if you do something bad with the center, then forget. So it's the weighted CRPS allows you to see that, okay? Because you can have this weight, and you can put more weights on different parts of the density of the forecast, okay? So that's just for one observation. You have density, you have observations, it gives you one value. What I do is I average this over the test set, over 3 months, okay? And in a sense, I am approximating the expected score. That's what we should do, right? Because we know that it's proper, so the expectation of the score will be always smaller. And I also compute the skill. Essentially, here the natural comparison is Bayes, right? Because if you cannot beat Bayes forecast, then what's the point of your method, right? Because if just forecasting everyone independently is better, then why all this copula aggregation, blah blah blah, right? Okay, so first the root mean squared error. So what do we see here? This is not CRPS, right? So it's root mean squared error skill. That's the base. Okay, I didn't introduce all the names. Essentially, this is bottom up. So I'm looking at the error with the aggregation. So of course you expect bottom up to become worse with the aggregation, right? When you go up. That's just the means. I'm just looking at the means, not the densities. Yes, maybe diag and shrink, not a big difference. Essentially the W. You remember the W I talked about before for Minty? Minty is, I forgot to mention it, it's the methods that SPY had, that's combine everything. Here, the difference between these two methods is just, we use the different estimator for W, not a big difference. Okay, so for the means, the message here is very simple, is bottom up is quite bad, because you forecast the means at the smart meters, it's very noisy. When you sum them, you have bad forecasts at top levels. However, when you combine, when you do the combination, you have a significant improvement in accuracy. So essentially the message is this P do something useful. Okay, so that's for means. Now, what I'm showing here now is the CRPS skill without any weights, so uniform weights. And this one is CRPL's tails, so I put a bit more weights on the tail. First of all, compare red and green. So this is expected because red is diagonal. So it wasn't important for mean, but for probabilistic forecast, it is important, right? Because go back to variance, the expression for the variance. If you assume diagonal and it is not diagonal, the estimate of your variance won't be correct, right? So that's why, this explains why the difference between red and green for the mean is not big, but then when you go back for probabilistic forecast, it's bigger. Okay, so that's the first one.
So the diag is that when you impose W to be diagonal, when
Yes.
it's not, right?
Yes, and the reason why this comment I think is important is because when you look at applications, people do mean forecast and they often use diagonal. It's fast, the inversion of W is very fast, and it doesn't make a big difference with estimating the entire covariance matrix W. But it's huge difference with probabilistics.
Okay, so I think, yeah, so it's Minty OLS or WLS because you have either ones on the diagonal or the weights on
Well,
the diagonal.
WLS is diagonal.
Yeah, exactly. Yeah.
Yes, I didn't use OLS because this one
Sure.
will be very bad. Okay, and our method is essentially the purple. And we also actually something funny is, I mean, what's the worst thing you could do is sample independently and sum, right? I mean, it's nonsense in well, except if everything is independent, but that's orange. So it's funny because, well, it makes sense. Things are so noisy and so complicated at the bottom level, you won't get anything from the dependence at the bottom. It's only when you go quite high in the level that you start seeing a gain by modeling your dependencies. I mean, that's interesting because imagine the amount of computational time you save knowing that things are garbage at the bottom. So you don't really gain anything from modeling your dependence. Yes, and then essentially with the tails, it just amplified the difference. It shows that indeed you model better the tail than here. Just a forecast example, which is just one example. So that's independent. So you remember I told you the bottom up for the mean was very bad. It's like some kind of bias in the mean. That's when we add the dependencies. Even if you add the dependencies, but your mean is bad, what's the point? So you are still bad. But then after you do the combination, you correct your mean, essentially. You have better mean predictions here. And that's base, right? Base is quite nice. At the top, oh yes, that's at the top. So it's very hard, it's very difficult to beat univariate forecasting of the top. Of course, you are trying to combine 1,000 forecasts from everywhere to improve the top. So you don't expect to improve it. That's just illustration of the type of forecast you get.
Why
Yes.
the confidence bands are so different from base, which is
It makes
quite
sense.
good,
No,
and-
it makes sense. Why? Because you assume independence here. So you didn't, of course, you won't get the right coverage here. You can clearly see that when you model a dependence, you have better, how do you say that? Coverage. And after the correction, then you are not too far from here. Yes, there is a difference, but you have increased compared to independent, right? Okay, so yes, we did also some simulations in the case where we know the truth, right? Because we wanted to check that indeed our method will capture exactly the true distribution, right? Because we don't do any theory here, we don't show that things are fine asymptotically, etc., but we do it by simulation. Okay, we show that the distribution of the p-values is uniform, and it should be uniform under the null. So yes, we did some simulations, but I won't go into the details here. Okay, so let me conclude. I didn't talk about everything, but there is a paper with all the details if you are interested. We want probabilistic coherent forecast. It's essentially a multivariate forecasting problem with hierarchical aggregation constraint. And we wanted to have multiple features in this algorithm, including exploiting the data everywhere, minimal distribution assumption, and scalable to large hierarchies. Just to remind you here why it's scalable, I didn't say it, because you don't need to model this big, this high dimensional dependence. You just need to model the dependencies at each node. Of course, if you have one case which is very bad, imagine you have a case with 1 million meters and 5, 5, 2, 2, and 2. This one is still going to be very big. So I'm assuming here that it's even. In terms of, I will give you some directions for those who are interested that I think would be interesting. Clearly, we didn't combine probabilistic forecast, right? The question is, how do you do? That's an open question. We have ideas, but how do you do this with probabilistic forecast? Instead of doing SPY hat, which is the mean, I give you a matrix with 100 quantiles for each row. Okay? Give me 100 quantiles for all nodes. It's difficult because the sum of the quantiles is not the quantile of the sum, blah, 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 and all that. Okay? That's an interesting problem. Or not even that. Imagine if y hat is not a vector, it's a density. It's an entire density for all of them. Can you do some kind of mixture in your combination? That's I think it's interesting. Other direction would be focus evaluation. Yes. What I did here is just I showed you the CRPS of all nodes essentially. I didn't aggregate this, right? Because if you start aggregating, you cannot just sum the CRPS. Otherwise, you need the combination. So that's also an open problem. How do you evaluate properly a hierarchy? Okay. For the mean forecasting, yes, I told you I have this algorithm, and it works well on multiple applications. So without unbiased assumptions. Regularization is also done here, but there are also directions of how do you make p-sparse, for example. In your combination, I want p-sparse, so I want to exploit the structure. And also that's something, I'm going to work on this next normally, is, so far, let me write something here. So far we have this. I have my vector, I sum, I get y. But imagine if you assume some kind of factor structure or something like Chiu-Yao or something like. Then can you do something like you have this? Then what? Oh, but you don't know A. In practice, you have to estimate it. But then you can call this by S prime. Then you go back to what we have. So there are some directions where you can do explicit dimension reduction. Instead of working with 1,000 smart meters, you reduce dimension to 10, and then it's extremely fast, right?
Does that end up being what Jetro was saying at the beginning of his talk, that you want to say, I don't care about having data from all the smart meters from the bottom? Would that end up being this kind of
Yes,
idea?
maybe dimension reduction with missing values or something like this, yes. But I'm assuming here I have the data everywhere. How do you, I mean, it's a natural thing. Think about it. You have a bunch of random variables and you are interested in the sum. The most natural things to think about is, yes, some kind of PCA, because PCA will do a weighted combination of your variables. The component is just a weighted combination. Yes, but you want weighted combination. So I think there is something there to do like explicit dimension reduction, because so far, even here, I am penalizing this objective. I add a penalty on P, right? Because this is SPY hat, and to reduce variance, I add a penalty on P. But still, it's not explicit dimension reduction. It's sparsity and all that.
Okay, well, what I was saying was more maybe to redefine the S in the forecast sense, is that maybe in your S you don't want to just readily sum all the components at the bottom, but
Okay.
more have a convex combination of what's happening at the bottom with as many zeros as you can, for instance.
Okay.
So you want to minimize the use of bottom information and maybe inflate some of the others or combine what's
Yes,
available.
that's in a sense what you do here if you add the lasso term, because you make if your P matrix is very sparse, that's exactly what's happening. You don't use many of them, right?
But then you inflate information from some others.
Well, that's the objective function. If you do this, let's say, if you do this, this is vectorization. So essentially, that's my matrix P, right? And I'm asking this to be sparse. What does that mean? That's my y hat. That's my vector y hat. If this is sparse, I didn't use that guy. I didn't use that guy. You could also think about different sparsity. Like you could ask the entire row, sorry, the entire column to be 0, which means nobody is allowed to use this one. If it's 0 for an entire column. Anyway, sorry, I talked too much actually. Well, yes, thank you very much. So that's the end.
Thank you.
Yes,
Some more questions?
Yeah, just a quick question. You said some of these lower level groups may have too many people measurements. So you can add additional levels in your hierarchy. Would that help?
Say that again. You mean add more bottom level nodes, or you mean aggregations?
Well, let's say you have 1,000 individual nodes in the in one group.
Yes.
and then you have the sum of these one houses. So this is not practical.
Okay, yes.
But you can divide the group into
Oh, yes, 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 got it, yes. Yes.
and so on. So doesn't, I mean, naturally,
Yes.
shouldn't it be a binary tree somehow?
Yeah, exactly. So there is another idea that you could add to maybe future directions. So far, the hierarchy is given to you, and everyone works on the hierarchy. One idea would be, don't work on this hierarchy, because this hierarchy is just what you want at the end. For statistical efficiency or whatever, you start from S, you go to another space, to another hierarchy, which is better for you because things are independent or whatever. You focus there, and then you go back to your hierarchy, and it's related to what you said. Yes, that's I guess would be an idea.
That was my point about hierarchical. So you assume you have a fixed hierarchy here, and we recently did some try on write a draft paper on that about I want to forecast something. So at some point in a hierarchy, in an aggregate of customers, and I don't care of the right hierarchy. I just generate randomly or with a machine learning algorithm, and it seems that you can significantly improve the forecast by combining those artificial hierarchy, in fact. And so my point was maybe if you can, for example, bag the hierarchy and then use the solutions and combine at the end.
Yes. So okay, that's a good point. Actually, I remember with this method, when I used the fixed hierarchy, I realized my method wasn't good. Even after taking the average over the test set, it doesn't make sense because it was so general and generalizing things. It didn't make a lot of assumptions. And I realized, indeed, I think in this hierarchical forecasting literature, people should average over hierarchies as well, because there is so much variation when you change the hierarchy. It makes sense because the type of things you need to model is different, etc. So that would be one explanation of why it works well. Or another idea would be SPY hat. It doesn't have to be a vector. So here, well, it could be a vector, but it doesn't have to be n. You could instead of forecasting all of them, just forecast, give 10 forecasts for each one. So you increase the length of y hat. That's fine. You just have more weights. But if you do that, you don't have to do anything. You just plug it here, and everything works, right?
And another point is that in the real network, you don't have the same quality of measurement at different level of hierarchy. Yes. And also you have the losses on the network, and so it isn't exactly the sum isn't exactly equal to what you measure. You have some noise, and so I think. It could be relevant to have, instead of having 0-1 structure in your sparse matrix, to have maybe quantitative information sometimes.
Yes.
Randomness there.
I would say this is more in the weighting of the errors. I think, because what does that mean? That it doesn't have the same quality. You don't trust, right? You trust more certain than others. So typically you do weighted least square. Those that you don't trust, you reduce the weight they have in the total. Right? So I would say here, you could do it by, instead of averaging, by giving a weight here. The way I see it is not in the S matrix, because S is just a structure. It's more in the optimization objective where you can take that into account. That's my feeling.
Well, but I think it's also in the S, because
Yeah,
if you have a loss, if you know but you're losing, say, roughly 1%, or you don't know if it's exactly 1%, then it's about the numbers in your S. You mentioned at the beginning you can plug there in other weights, and it's about estimating these weights, I think so.
Here, S, so if you go back to here,
Yeah.
S defines your hierarchy, okay? So it tells you that I want the sum of these guys. I want the sum of these 3. I want the sum of these 2, okay? So it defines your hierarchy.
Yeah, but it's almost like there's an extra house or something that doesn't have a meter but has some consumption or production that represents the losses.
Yeah, that's just so you can model the relationship.
Ah, yes, okay, you want to see it not as a constant, you want to model something here in S, yes, maybe? Yes, maybe. Well, actually, something related to that, for this application, we had something related to that, but not similar. Our S matrix was stochastic in a sense, because it was changing over time, things like this. It might be related to that, but yes.
Yeah. I think in practice as well, you'll have metering at different points in the hierarchy, and I suppose it's not even like a forecasting problem, it's almost like a state estimation where you have sparse metering across the hierarchy and you want to fill in the gaps. I think it's a really
Yes,
nice
okay.
problem.
Yes, no, I
Very
think
closely
there are a
related.
lot of problems, and also I didn't mention another one that I discussed with you. So far, all these series are in discrete time. The natural question would be, if you continue disaggregating this, at some point you are in continuous time, and the question would be, can you combine like temporal point process models for the continuous time plus discrete time models? Can you define objective function that does that? That would be great. Imagine if you have forecasts in continuous time that are coherent with the forecast at the top. I mean,
Yeah, but that goes towards what Jetro was showing with the wind farm. Also, the turbine data you can have at 1 second in lots of places, but then the scatter for the wind farm they collect at what or they transmit at 5 minutes or 15 minutes, or so we have also this mix, as you say.
yes,
It's almost continuous
Okay.
time at the turbine level, and
yes, and here you
the
have
effect in
to
space and
define
time
the
also.
problem. Time of event becomes relevant. Like imagine here you have a problem where you are interested in time of event. You want to forecast time of event instead of YT, the amount of IT. I'm interested in time of event, and that's, I believe it will be interesting to investigate.
So yeah, you doesn't exploit really the time series structure of your meter here.
It's a good point, actually. If you look at the way we do it, SP, look at P. Although P is the covariance matrix of the historical observations, this is contemporaneous. The P. We are at T, and with the combination, we don't really, because we're assuming everything is conditional on y hat, and we're assuming y hat has already modeled the temporal things, right?
But maybe related to, you already say there is maybe connection with what Shiwei proposed. Maybe having something like a cross correlation between the different hierarchy and the meter, adding that
Yes.
after should be interesting.
Yes, and also something that's related to quantize is, because you mentioned Chiwi also, if you give me in this hierarchy, if you give me quantile forecast here, everywhere, what does that mean to be coherent? Just define it. Can you define it mathematically? I mean, when you play with densities, it's just the convolution of the density should be equal to the densities at the top, so you can write it mathematically. Now, can you start from there and say, oh, but the density is just and then with the quantiles and define it mathematically? Because clearly we have probabilistic forecast, we have mean forecast. The only one that's missing in this framework is quantile regression or quantile forecast. Directly, I mean, I'm not saying you produce density and then you extract quantiles. No, your optimization. So you change this optimization. I want to see here. I want to see quantile loss, pinball loss here. I want to see that. So we have some ideas, but it's not yet. It's a very good point. Sorry.
No, that's a very good point, actually. I was just thinking of it then.
Cool.
Okay, any other question or? Never. Thank you very much. All right, well, I would propose we take a break for like 30 minutes. We start again at 3:40 in the discussion room downstairs. Hopefully still with a bit of energy. You've been tough on us today, guys.
Was an average. So yesterday was as complex as today.
I think the accumulation of everything. My neurons are slowing down.